So the key question is 3137 states that if you want to take OSPF router, ABR, or take an OSPF router out of operation, you can advertise max metric, which is great. But then the question is, what do you do with the type 3s that you're creating if it's an ABR? Do you need to set them to max metric? Can you, or do you not care? When I first read this, I thought maybe you need to set them to type 3s to metric max as well. But if the next hop is set to me and my type 1 is set to max, then it doesn't really matter, right? It just
exactly. So it's just to you. It's not the summary you generate, because summary is generated by you being ABR, and I'll go through you, right?
Yeah,
so
but
if metric to you is set to infinity,
but in the meantime,
I think
we have a show to do. And we're live.
Yeah, quit being the voice of sanity. We're enjoying this conversation.
Yeah, that's right. Hey, good day, fellow nerds, and welcome to another episode of Between Two Nerds. And I noticed in our introductory slide, we actually had Russ as nerd number 3, correctly positioned between nerds 1 and 2. And but this conversation started off before we went live, just with us talking about IETF, which is going on all this week, and naturally an IETF discussion has to start talking about RFCs, I guess. But anyway, Jeff Tansura, good to see you again.
Good to see you, Jeff, too. Always.
And Russ White, thanks for I think you are our gold star guest. I don't believe we've had anybody else on for 4 times in a row. And
Tony P, I think we can.
What's that?
Tony P, probably close.
Tony P just has to beat me at everything.
Yeah,
so,
I think it was Tony P on here 3 times or 4 times. Well, anyway,
so whatever his number is, we got to do one more.
Yeah. You know, it reminds me, there was a Saturday Night Live skit years and years ago where they were supposedly showing backstage all the veteran guest hosts that they had for many times, and man, I can't remember. I remember Paul Simon was on there. It was whoever the new guest host was, and all the veteran hosts were lecturing the new guest hosts on he hasn't been on enough to qualify for their little club yet or something like that. So anyway, you definitely qualify for at least one of 2, if not the only one of the guests that have been on for and put up with the 2 of us for quite a while. So we are continuing our discussion of Jeff and Russ's book on navigating network complexity. And I guess to kick things off, Jeff, you had in our last show, we were talking about operational complexity, and you had mentioned you had some slides you wanted to share about that.
Yeah, so this is something I'm kind of preparing for another event, but I would really like to share with you some ideas about how do you deal with complexity at scale. And okay, here we go. Can you see my slides?
Yes.
So reliability at scale is a constant struggle. We're all familiar with this stuff. It doesn't include Facebook, right? Which have somewhat different set of issues, but practically at hyperscaler scale, you need to start thinking about how do you compartmentalize your complexity, how you reduce it in particular cases, hide in another.
25.
Yeah, so we are pretty large. We are, as you know, I'm employed by Microsoft.
Number, so 25.
Yeah. So I'll keep it to Microsoft in this case. We are building really large data centers. Our next generation data centers are going to be 1.2 gigawatt or around this number. to give you some impression what it is, whole electricity provided to city of Dublin is 2 gigawatt. So it's more than half of Dublin, just to put it in the right perspective, right? So this is pretty much how it looks, and it's getting larger and larger.
Where's the airplane?
Yeah, so obviously large scale comes with large problems. And when you find a problem, it's right for this particular second, because there are so many other things going on, and it's so interrelated to each other that practically you need very, very complex system to correlate, to find relationship between different issues. So this is really kind of an introduction to why we need to reduce domains, why we need to provide degree of abstraction and comparison. And changes do cause outages, right? We've seen.
Yeah.
So again, I'm talking here about Azure, but this is pretty much how every data center in the world is built today. It has a rack. Rack is connected to a number of spines and forms a pod. Pods are interconnected by next level we call super spines, and this is how your data center is going to look like. In order to interconnect data centers, you will use DCI technologies. There are many of those, usually MPLS of some form. And this will form another kind of level of networking in hyperscaler terms, usually called availability zone. Availability zone is usually dictated by distance and RTT. So this is pretty much how things look like. Within region, you usually have RTT within particular limit to make sure that your consensus protocol works. So when you've got consensus running across them, it should be fast enough to address it. When you do replication for particular workloads, it still needs to work. So usually we are talking about something up to between 70 and 110 kilometers, right? So, and this is where I'm coming from. Practically, what you see in such a large network is non-stop set of changes. There's always something that's broken, needs to be updated, needs to be upgraded, needs to be changed. So unless change in particular place has effect on state in another place, it becomes a global problem, right?
Mm-hmm.
In order to avoid this, you need to provide self-contained boundaries. So in the way you do it in data center, you've got very well-defined boundaries. It's your rack, your pod, and your data center. When we are talking routing, usually it means aggregation, summarization, and route hiding, which we describe in book in many details, right? With trade-offs. When you hide amount of information or aggregate a route, on one side, you hide all the changes within aggregate, right? If one of the routes disappears, you won't notify your neighbors because you can still reach whole subset of routes, right? Which on another side could lead, best case, to suboptimal routing, worst case to black holing. That's why, and we discussed it before on our early shows, summarization in data center is something you really need to understand, because on next hop failure, you might start black holing. Mm-hmm. But practically, you need to provide self-containment boundaries as much as you can. This is the only way to be able to run your changes nonstop in different areas, because you know that when you change something in your pod, it's not going to affect changes in pod in another data center. When you change something at your rack level, same here. So all these changes are hidden at particular levels. And this is fundamental to scale. And I just included a slide from Peter's presentation a couple of weeks ago, either Facebook or Meta BGP design. You see how they aggregate, and that's exactly what I just presented. You've got /128 at server level, at track level, you aggregate /96, and at pod level to /64. Potentially higher up, you can again aggregate to something like /54, right? So this is exactly same story, and given Facebook size, they're facing same issue. So this is pretty much where I wanted to bring you by showing this. There is no way to avoid complexity at scale. The only way to make it manageable is to reduce domains, to reduce propagation of change and really blast radius.
Then you've still got leaking between domains. I mean, essentially, you've always got leaking between domains, right?
Sure, but imagine if you leak /64 between different pods, whatever happened within your pod doesn't affect /64 advertisement unless you lose last contributing route. Then aggregate should disappear, right? So practically, you've completely hidden all the, I mean, I wouldn't call it stability, all the changes in dynamics within the pod, because outside wall sees single route.
So, Jeff, what are the trade-offs you would say in this design? As we all know, there are trade-offs with everything. What are the trade-offs? Do you have any thoughts on?
Suboptimality. I mean, the less information there is, the less information there is to take a good decision upon, right?
Mm-hmm.
So practically, by aggregating, you are removing the degree of information you are propagating, right? And practically, imagine part of your fabric goes down, particular plane goes down. If you would still propagate disaggregated routes and even attach a bandwidth community to them, you would be able to start and actually load share traffic across planes that have more capacity. But if you only send aggregate route, probably you wouldn't even know there is some instability within the network, right? So by removing this additional information about network and additional details, you actually remove visibility into what's going on inside. And this goes back to very fundamental design in link state protocols. That's why we have areas and levels, really to hide this, because what we just discussed about OSPF, you don't propagate type 1s, type 2s. You only aggregate and propagate type 3s. So in other words, you actually hidden a lot of information from area, and it's done per design, right? Because you cannot scale indefinitely if everyone talks to everybody else. The abstraction of an area is its aggregate.
Okay.
And
routing black holes, do you see any of that kind of stuff in this kind of design? Because you've done so much aggregation. So, right. So this gets down to design complexity, right? Which is what Jeff D wanted to talk about, is that when you do design, you end up with these kinds of trade-offs. And this is just because it just works that way. And you've got to think about what those trade-offs are. You've got to go find them because they're not always obvious, unfortunately.
I can remember discussions of route aggregation, probably going back 25 years or more, where people will talk about, well, the trade-off is if the more route detail you're advertising, if a route is lost, the decision to not that network is unreachable can be made much deeper into the network, as opposed to having to go to all the way to whatever your aggregation point is, only to drop packets at that point. And 25 years ago, that seemed to matter. Does that kind of thing even matter anymore with the kind of bandwidth we have these days to just say, yeah, traffic is still going to go to some aggregation point a long way away from its origin before it's ever dropped. But do we care?
Well,
I think we do. I would take another angle. Let's take. Sorry, Russ, do you want to continue or?
No, go ahead. I'll let you finish, and then I'll tell you why.
Let's take not aggregation but hiding. And the probably best example is BGP. So BGP by default will run best path and advertise only best route, right?
Mm-hmm.
It will suppress advertisement of all the routes that are not best ones, right? So we've introduced add path to provide not only the best route, but next best, next best, and so forth, right? So the computation is very simple. You compute your best route, then you remove it from the graph, and you compute next, and so forth. So in a way, we are disaggregating, not right word, we are removing hiding of less optimized route. We advertise them as well.
Mm-hmm.
So on one side, there is more information available. And for example, if you use same bandwidth community, it's important because now you will have different next hops with different bandwidth communities that you potentially could use to do weighted load sharing. On another side, you are using much more memory. So eventually, you will just run out of memory. And when you enable a path of 8, I can tell you, you're using gigs of memory for BGP. I'm observing it on a daily basis. So again, more information, more resources, or less information, but less optimized forwarding. Russ?
Okay.
Yeah. So I think the other reason you care is because of jitter. And everybody really downplays jitter in their networks. They don't think about it. Even in 5G, we hear mostly about delay and never jitter. I've had several conversations around this, but to me, jitter is the real killer in application performance. Because if you know that your network could deliver your packets in 2 milliseconds or 500 milliseconds or even 2 or 3 seconds, then you've got to set your timers up for failure in those time frames. And that gives you this problem of, okay, I'm running along, everything looks fine to me, but now I have these packets that are backing up in the queues, and I'm building up buffer someplace because I got a lot of packets in flight on the network.
Yep.
What do I do as an application? Do I just sit here and take it? Or do I say, okay, I'm going to drop the session and start over, or I'm going to ask for retransmits? What do I do? And so when I see a route change in the network, what that looks like to the application is jitter. Bam, I was getting 50 millisecond time across the network. Now I'm getting 200 millisecond time across the network. And the application's got to be able to figure that out. And so to me, when you talk about, does it matter because we have all this bandwidth? Yeah, it does matter because I'm adding hops.
Yeah.
And that's why one of the great things about spine and leaf fabrics is that you end up with basically equal cost paths, so many equal cost paths that it never takes you longer. In fact, all the traffic between an ingress and an egress port in a 3-stage costs us exactly the same number of routers or number of devices. In a 5-stage, it can either cross 1 or 2 devices or 3, however you count it. But there's only a one hop difference, whether it's in pod or out of pod. And I think that makes a huge difference in your ability to manage applications. This is something we forget with virtualization, right? We lay virtual topologies on top of stuff, and we say, "Oh, it's not a big deal if it has to T-bone through a couple of firewalls to get between VRFs." Well, yeah, it does make a difference.
Yeah.
This is, and the complexity of the path is a lot worse. Now, on the other hand, spine and leaf fabrics bring their own kind of complexity to the table, which can cause other issues.
And practically, it's backwards proportional to RTT. So the larger the RTT, the less visible the jitter, right? Because it amortizes across, and practically application should be able to sustain reasonably large jitter, either by buffering or doing some form of reordering before feeding the application, because no application can deal with out of order packets. If you are thinking about data center where RTT is close to 0, and most people don't care about delay, we do care about jitter. Yeah. And this is just for TCP traffic. Imagine your traffic is lossless, something like RDMA. So when your RDMA receiver actually receives out of order packet, it will decide that packet had been dropped because it's out of order, meaning he didn't receive packet before. So it will ask sender to resend. And depending on RDMA implementation, resend might mean resend memory page of 4 gig. Right? So it could be catastrophic if your links are overloaded. So jitter in general is much bigger problem than constant delay.
Yeah. Yeah.
Oh, pregnant pause here. Sorry, I
When
was.
is this pause going to give birth?
Yeah. So, I'm just looking at some of the notes that I jotted down from your chapters on design complexity and managing design complexity, about midpoint in the book, maybe. Shows how much material there is in this relatively small book that that you've got in there. But one of the points you made around design complexity is the idea of network stretch. For the sake of everybody watching, can you define that and how you measure stretch in a network? You hear people talk about it a lot, but
yeah, that's what happens when you send your intern out with his cable stretcher to make the cable longer, so it'll reach between two things that you really want to be able to get between. Now, stretch is something that comes out of the world of mobile ad hoc networking originally, and wireless networks, which goes back to the original. I mean, the whole concept of things not taking the shortest path. And so stretch is it's a very loosely defined thing. There's not a lot of, sorry, I was just checking the comments. Nobody's making any comments.
yeah.
Drag them in from the bushes and get them out here to make comments.
Yeah.
Anyway.
Navissa is there. I got to say hi to Navissa because he's a very faithful viewer here, and he said hello to everybody. So hello back.
So the very loose concept is the differential between what the optimal path would be for some version of optimal versus what the actual path of the traffic is. And of course, optimal being when the network is working perfectly, there's no failures, there's nothing going on, you have no policy implemented saying that you want to avoid a particular path, anything like that. It's like just the shortest path, the highest bandwidth, lowest delay path through the network. And when you create policy for load balancing or traffic engineering or whatever it is, you typically increase stretch in order to implement that policy. Traffic engineering or traffic steering is perhaps the most common example of this. I have one path that's low delay and one path that is high bandwidth. And the low delay path is lower bandwidth, not because it has fewer hops. And so I push FTP traffic to the higher bandwidth path, even though it's not necessarily optimal. It's not the shortest path through the network. But I do that in order to get the traffic for a policy reason off of that shortest path and reserve that shortest path for something else. That would be an example.
But optimality is subjective, right?
Yeah, it's
one maximum.
You broke up a little bit there, Jeff T.
I'm.
Are you doing that on purpose?
No.
So
I'll be
it is subjective. It is subjective to some degree. This goes back to state optimization and surfaces. And sometimes you have different things you're optimizing for.
Mm-hmm.
And you may increase the stretch in order to optimize. And jitter, when you talk about jitter, you're often talking about variable stretch. Mm-hmm. Routing protocol convergence is variable stretch. Again, going back to the firewall example, when you trombone traffic through a firewall in a data center fabric, you're intentionally increasing stretch by adding hops to the path in order to solve a policy problem. And so policy often results in longer paths, suboptimal paths from a pure routing perspective. In fact, one way that I look for policy in a network, people say, what does policy mean? I'm always like, well, one thing that I look for in terms of policy is, are you implementing something in the network that changes the path from what it would normally run?
Yeah.
Right? If I just ran SPF, I would get path A. If I run SPF plus this policy, I get path B. That therefore it's a policy.
Mm-hmm.
Whether
A
it's
very vivid complexity here is trying to optimize towards multiple goals, right?
Mm-hmm.
I mean, multidimensional optimization, very complex topic, and if you try to do it in parallel, it's going to be hard, right? Be complete.
Yeah. NP complete.
Yeah. I think what we are trying to do is don't run them in parallel. We run them serially. For example, to compute path that has lowest hop count and highest delay, we would metrics and tune all the nodes that don't comply with it, and then run another. If you try to do both, it really doesn't work. So, as you know, recently we virtualized IGPs by doing what we call flex algo, meaning not only running shortest path, it could be lowest, highest bandwidth, or any other. We've got 3 or 4 different metrics defined there. But pay attention, you define only one per flex algo. You cannot run 2 flex algos on the same topology. It could be different topology. And for a reason, in working you need to keep it simple and everybody agree on what you're trying to achieve or trying to optimize towards. If you try to mix them for this and complexity associated with it.
Yeah. I'll give you 2 other examples of this, actually, of the NP completeness of multiple optimizations. One is the EdgeERP. So a lot of people don't understand why EdgeERP creates algorithmically creates a single metric. It has bandwidth and delay that are carried separately, even though they aren't dynamically calculated, contrary to popular belief. But they are there. So first of all, why not calculate them? Why not discover them dynamically? But that's because of hysteresis. And the second problem is why do you combine them into a combined metric using some sort of formula? And the real reason there is because calculating multiple formulas is NP complete. You can't do it. And I'll give you a second example, which is kind of humorous, which is that this is why BGP has wedgies, because BGP is optimizing for multiple metrics. Even though there are tiebreakers, you still get in situations where the AS path is more important, or the med is more important, or the internal metric is more important, or the local pref is more important, or the weight. Mm-hmm. And because various people can play games with different metrics, and because of route reflectors, and you have aggregation of information or summarization of information at route reflectors, it can turn out that you end up in a wedgie where you just constantly are recalculating between 2 autonomous systems over what the best path is, because you have multiple optimization points you're trying to make, and everybody does different emphasis. So these are just examples of, you just can't optimize for 2 metrics.
Beautiful talking about BGP oscillation. It's 5,000 something, right? And then we scale in really networks. It's the result of what Russ was describing.
Yeah. And so, the way we get rid of the oscillations is to eliminate the second metric.
Yeah.
Or everybody, or, always compare med. Oh, how do we get rid of the oscillation? We always compare med. Well, what's that doing? That's actually producing determinism, so that now you have a fixed set of things that you're doing. So that's how you get around it.
And you can areas for too. As an example, clone network. when you advertise routes, everybody else will learn routes from all leads. So in some cases, you will advertise them back and forth, right? And funny enough, some vendors will choose route, while another vendors will choose route with router ID. There are two RFCs defined ways of doing so. One of the spines will never send traffic back to a leaf based on who is the best route, because per definition, going to, even if you configure like allow your own ICE. So practically it creates non-determinism in how your fabric is sending traffic based on this method well defined and different parameters. Well, I mean, you really need but if you're running multi-network, that different ports behave differently.
So when we go back to Clo fabrics, we talk about design complexity, right?
Yeah.
And we talk about trade-offs in design complexity. And I said one of the really great things about Clo fabrics is you have all these parallel paths that allow you to not get the jitter when things fail. Not necessarily. I mean, things could loop, but micro loops always happen with link state protocols, and packet drops always happen with distance vector protocols. But regardless, you have these two things. The problem with a Clo fabric is it's still a complexity trade-off, because from a control plane's perspective, a Clo fabric is extremely complex to converge on. This is why BGP natively, if you build a large enough fabric and throw enough routes at it, BGP just won't converge on a Clo fabric, a 5-stage, a butterfly, just won't converge. You can leave it for days. Feel free. Doesn't matter. You just won't converge. So you have to play tricks to make it converge, play with AS path stuff and do all sorts of stuff, which is all fine. But that just speaks to the complexity of the control plane on top of that fabric. So you're making a complexity trade-off when you choose a 5 or a 3-stage fabric, spine and leaf fabric. The one side you're getting is you're reducing your jitter. You're getting a lot more fan out for your ECMP. You're getting a lot more paths. It's really cool, but the extra paths can cause complexity at the control plane level that just you have to work around, and that's okay. There's nothing wrong with that. It's just a trade-off. It's just the way it works.
When you think about overall complexity, you really goal your towards, because if you don't, eventually it's not going to work. So again, taking BGP fabric, imagine, usually people consider great restarts a good idea, but it defeats of multiple paths available, right? You want to use graceful restart. You want to fail. So any decision you need to take to figure out that you don't need what normally would make sense someplace else, right? You optimize towards the fact that fail the path that becomes unavailable, even partially unavailable, soon as possible, because you've got 8 or 10. See the bit? I'm seeing messages.
Oh yeah. I think just in the background, just mentioning your microphone is breaking up really bad.
Let me see. I'm using right mic.
Seems to be getting a little worse as we go. As you add complexity to your conversation, your microphone is breaking up more and more. Yeah, something you mentioned earlier, Russ. I mean, I kind of keyed on that, and the conversation went a little bit differently. But you were talking about, when you go to a Clo fabric, a spine and leaf fabric, you're putting complexity. You're taking on complexity in a different way. I don't think you said it exactly like that, but it just reminded me of one of my favorite statements that you might have been the one to have originally said it. That you can't really reduce complexity. You can only move it around. And because when you first say, oh well, there's complexity in clove fabrics, when you compare that to what came before, with 3-stage hierarchical fabrics or more,
Oh my goodness, those were
you look at the diagram and it's like,
yeah.
well, clove fabric, it looks so much simpler. And yet, from what you're saying, it's well, you're taking that topological complexity and you're moving a lot of it into the control plane.
Well, I would say it's a straight trade-off, right? It's just a straight trade-off. Um, the beauty of a spine leaf fabric is originally by design, the fabric doesn't have any intelligence. The
Yeah.
fabric itself just looks like an Ethernet switch, and that's just what it should look like.
Mm-hmm.
Now, we being network engineers, and the problem with a traditional hierarchical design in a data center fabric is that it really constricts um, your applications need to understand the network because it's not an Ethernet switch from their perspective. It's a very complex layer 3 with all sorts of, if I take this path, it goes this way. If I take that path, if I'm 5 hops away, things look different to me from an application perspective. The spine leaf fabrics, whether they're butterflies or clothes, you don't have any of those problems. It just looks like an Ethernet switch from the outside.
Mm-hmm.
And in fact, if you look at a lot of switches today, multi-FE chassis boxes, if you might want to call them that, or just multi-FE boxes, forwarding engine boxes, the internal fabric is a clo.
Yep.
And so it just looks like a switch. So that's very beautiful from the outside. From the inside, yeah, there's trade-offs here. There's gray failures. There's law of large number issues. There's just stuff that you run into with these truly large-scale fabrics. I think Jeff was talking about that in the very beginning, is that scale is its own kind of challenge. And that drives you when you build scale, and Jeff might want to talk to this more, that drives you as you build scale to really focus on simplifying your control plane and simplifying in other areas, because the human mind can only handle so much complexity. And you just can't understand it at some point. There's too many moving pieces.
Yeah, and you can even get that. You can even get clo topologies going all the way down to the silicon level, all the way into the ASIC.
Absolutely.
Right.
So, how's my mic now? Better?
A little far away, but better. You're not breaking up anymore.
Okay, I'm talking to my camera. Actually, it has my. So, I was going to say, yeah. So, if you think it's complex today, we are looking into new ways to propagate network state into routing. So, just yesterday we had routing working group session, and the last presentation was focused on HPC C++. It's an SIGCOMM paper. There's a draft. Practically what it does, and the problem here really is that ECMP in Cloud Fabric works beautifully as long as there's a significant difference between flow size and interface speed, right? Bin packing works pretty well even with basic ECMP. However, when you start reaching order of 4, so for example, your flow could be 100 gig and your upstream is 400 gig, suddenly stuff stops working. On any CMP collision, so collision means that you are sending more traffic, you're hashing more traffic that your interface can take. Meaning, if you have 100 gig flows, you'll hash 5 of them into a single interface, which leads to 20% oversubscription and complete lock of any traffic on this interface.
Yeah.
Right?
I mean, Linda had that presentation, right, about Anycast and load sharing, and how,
Yeah.
you still end up with like imbalances, and you're using this stuff to make it work better, and it's still, you end up injecting state back into the network to try to solve that problem.
So, but what we are trying to do here, or authors trying to do here, is actually to measure condition of the network throughout in-band telemetry and feed it back into routing and actually sender and receiver. So now amount of data, while data is high fidelity, we are still a bit slower than the way packets are going, because in order to get forward, you need to get back, right? Because your data flow is going forward, but your signal is actually going back. So you are one RTT behind, at least. if not more.
Yeah. Right.
So the
Conceptually, how much
complexity
of this?
associated is huge.
Yeah. Conceptually, how much of this goes back to the old ideas of? It's kind of funny to think that they're old ideas now, but the old ideas of SDN. Where you separate the because you are pushing just in modern network topologies, you're pushing complexity into the control plane. Let's separate the control plane from the forwarding plane. Centralize, the forwarding plane remains distributed, but then you centralize the control plane where
I think it's a
you
very good
can.
topic.
Yeah.
So
Yeah.
I would say that so we are really talking about admission control in this case, right? And since you've got end-to-end view, you can actually using some form of source-based routing and some other ways to admit only amount of traffic that network is capable of transmitting, right?
Mhm.
And if you look at technologies, probably the best well-known SDN technology for I don't know high performance computing is really InfiniBand. InfiniBand guarantees lossless delivery by having the centralized view into the network. However, InfiniBand means you pay more, you are bound to particular vendors, and there are not that many that support InfiniBand. So the trade-off here is fully vertically integrated proprietary solution versus vanilla Ethernet fabric with BGP and pretty much any vendor, any box. In one case, your SDN control management plane take care of lossless characteristics and admission control. In another case, your total price is order of magnitude less, but now you need to take care of emulating this lossless behavior, which is completely alien to Ethernet in general, especially to packet networks.
Yeah.
So different trade-offs.
Yeah, and I think part of the danger of an SDN, I think what we hit that people don't realize is that it's very, very easy to think that you can throw the complexity over the cubicle wall and hand it to the controller and it just all works.
Mm-hmm.
I don't care how much I pile into the controller. It's so easy to sit in a meeting and say, we'll just let the controller handle that. Oh, that's a problem. Okay, we'll toss that to the controller without starting to realize that, it's the same thing with BGP to me today, right? We say, we'll throw it at BGP. It's not a problem. We'll just throw it at BGP. Well, when your BGP implementation gets to be 200,000 or 300,000 lines of code, you start wondering, maybe this wasn't the best idea.
To begin with.
No.
And funny enough, at scale, you're hitting exactly the same problem. So you cannot have one controller because single point of failure.
Yeah.
2 is not enough. 3, you need to figure out who is going to be the leader. Multi-regional, now you need to agree on synchronization. You're running same cap problems as before with BGP. The providing consistency at scale is really, really complex. So you just remove this complexity from your network into your management plane and SDN controller, and guess what? It didn't get any easier. If anything, it got more complex.
Yeah. And so this applies though not just to protocol design, but also just to design of networks, right? That you face this constantly, and you may not realize it unless you externalize it and you sit down and think about what you're doing. And this is where the state optimization surfaces trade-off kind of helps you just think it through. Just gives you a model to say, all right, if I'm going to optimize over here, that means I am increasing state. If I'm going to decrease state in order to optimize the operation of the control plane, that means I am going to have some sub-optimization someplace in traffic flow. And I need to focus on figuring out what that's going to be and whether or not that's acceptable.
And I think there are great examples of running particular designs throughout this very simple formula that's defined in the book, right? So actually, there are a number of people, and I'll provide links later, who use formula defined in the book to run designs through it and really to analyze from this perspective. So I've got the triangle of state and other attributes associated with complexity, and then definitely analysis of each surface.
I was just looking up at the time now. I'm enjoying this conversation a lot. I think we could keep going for like another hour, but I just noticed that we're almost out of time here. Yeah, but I also don't want to cut everything off right in the middle of.
Well, there's another show to be had here, Jeff.
I think we could just keep this. We're going to have to rename this show to Between Three Nerds and just make you a permanent host here. But yeah, I mean, let's definitely continue this conversation. I hope everybody that's watching is enjoying it as much as I am. But and I hope you guys are enjoying talking about it as much as I am. But in the meantime, we do have to stop at some point. So for now, Russ, thank you once again for joining us.
Thanks for having me on.
And Mr. Tanzura, always a pleasure. Don't get to see you as often as I used to when we were both in the same insane asylum, but nevertheless, it's always fun. And for everybody that joined us, thank you for joining us. And as usual, please do like us on Facebook and subscribe to us on YouTube. And we will see you in the next show.
Thanks, everyone. Russ,
Thanks,
thank you
everyone.
for attending. Jeff, always